Um, the other time we have discussed the problems of higher derivative theories, because higher derivative theories solve one problem, their normalizability, in the case of gravity, but they create much worse problems. They violate unitarity at the level of quantum field theory, but they also have problems classically with the fact that, for example, if you want to rephrase the system as a system with no higher derivatives and more variables, then you will have an energy that is not bounded from below. So that is an instability. That is the same minus sign that you see here. You will see it in the energy. But there is also an important case which is can be used as a prototype to study what happens, which comes from classical electrodynamics, the Abram-Lorentz force, which is described an effective field theory there, described by means of higher derivatives. So since it is an effective theory, one could not care, but in the case of higher derivative gravity, it's not an effective, it's an analog equation that's not effective, but fundamental. So you have runaway solutions, but there is a way to get rid of them. And that's as follows. So let's write this equation in a slightly different form. Which is as follows. So let me collect an operator here, 1 minus tau d over dt A. And now take this operator and invert it, so you get MA is equal to 1 divided by 1 minus tau d over dt fx. So that's a sort of average of the external force by means of a green function, which would be the inverse of that operator. We have done nothing so far because you see that this inverse has a zero, as a pole, and that is the extra degree of freedom that we are not losing. However, there is a unique way to choose the green function so as to have a correct limit for tau going to 0. Because tau, remember, is the electric charge, and you would like your theory of electrodynamics to describe something that recovers the limit of no electromagnetic interactions when you switch off the electric charge. So you would like to have the correct limit tau going to 0. And then correct tau going to 0 limit implies unique green function. What is this green function? Now I write the most general solution and the particular solution. most general solution is MA equals minus 1 over tau integral, let's say, from minus infinity to t dt prime e to the t minus t prime divided by tau external force calculated in t prime. And then the arbitrary constant, this is the green function basically of, here you can check that when you apply 1 minus t tau d over dt, you get the delta function. You can check that this is a solution indeed. But this is a particular solution, so you get one arbitrary constant, and we isolate it like that, and that arbitrary constant multiplies the runaway solution. Why did I write it in this way? Here you could put the constant you want instead of minus infinity, but I put minus infinity to show that this equation has an equivalent form here, which is runaway solution plus something here that you see is a kind of average of the force, but it involves only the past, because the integral is from minus infinity to t, so there is no violation of causality here. You have an equation where it's enough to know the past and present of your force, but not the future. And then you have the runaway solution. If you want a solution that's regular for tau going to 0, then you need to fix this constant here or there. The extremum of integration of that constant must be fixed in a unique way, because you see this is an essential singularity. The runaway solution does not have a regular limit for tau going to 0. That's an essential singularity for tau going to 0. But in that case, the special solution is this one. 1 over tau integral from t to plus infinity dt prime e to the t minus t prime divided by tau f external t prime. No arbitrariness is there, but the integral now involves the future. So you need to know the external force in the future to write down the equation. That's a violation of causality. But actually, you do not need to know a lot of future, because there is an exponential in front, and so what you just need is a little bit of future. And numerically, this tau is 10 to the minus 23 seconds. And in classical electrodynamics, these effects are covered by quantum effects, so you never have any problem, actually, even if you use this equation. Why is this regular? You can show that this is regular for tau, if you expand in tau by making a change of variables. Let me call the argument of the exponential minus u. Minus u will be t minus t prime divided by tau. So you have MA equal to what? So du is equal to d t prime divided by tau, which is what you get there, dt prime divided by tau. And so you get an integral in the variable du, and the integral goes from So t prime was going from tau to plus infinity, when t prime, from t to plus infinity, t plus infinity. So when t prime is equal to t, minus u goes to 0. And when t prime is equal to minus infinity, plus infinity, when t prime is equal to plus infinity, u goes to plus infinity. And then the exponential now becomes the exponential of minus u, and then the external force becomes the external force in t prime. So here we have t prime equals t plus u tau. Yes. So now you see that the exponential is decreasing in the entire domain, and so you can expand in powers of tau. If the external force can be expanded in powers of tau, you can expand the entire formula, and that is regular when tau goes to 0, because for tau going to 0, that you just factorize an integral that's equal to 1, and you recover f equal ma. But that's the only possibility, because the arbitrariness, however, instead cannot have a regular limit for tau going to 0, because it's an essential singularity. So there is only this possibility, which means that you can get rid of the violation, the serious violation of, say, unitarity, by paying the price of having a violation of causality. Actually, this is a violation of micro-causality, because it occurs only for very small intervals, time intervals. So it does not affect causality at larger distances. Now, in the second part of the course, we will see that it is, although it's non-trivial, but it is actually possible to achieve the same goal in quantum gravity. Since causality is not a strong principle, and indeed in quantum field theory there isn't even a satisfactory definition of causality, not even for the standard model, and since one must be prepared to accept the fact that quantum gravity certainly has to change something new to say about the nature of space-time at small distances, well, that's what it is, and by means of that, it does work. Now, we end the first part of the course with the last argument that will take today possibly half an hour or something tomorrow, and that is the Unruh effect. What is the Unruh effect? It describes a detector that moves with some acceleration, and what happens? It detects the presence of particles even if in vacuum. This is a quantum effect, and the spectrum is a black body spectrum. This is an interesting calculation that involves a very simple description of what gravity, quantized gravity is. So let's see how it works. So first, how do we describe the detector? We describe the detector as a point-like particle with discrete energy levels. Like an atom, hydrogen atom, in the discrete part of a spectrum, and it detects something when it gets excited. So that's enough to detect something. It will start to be, initially it will be in the ground state, and then we'll see when we accelerate it what happens. Now we should couple this to gravity, and we couple it to a scalar field by, for simplicity, we couple it phi, but that is a quantized scalar field. So let us choose some notation. We call tau will be the proper time of the detector. And x mu of tau, since it is a point-like particle, it will have a certain trajectory. That will be the trajectory of the detector as a function of the proper time. And since it is accelerated, we will describe it by means of the hyperbolic motion that you know is the relativistic analog of the naturally accelerated motion. We will give the explicit formulas later, but that is its trajectory. We describe the interaction what we are accustomed to call J mu A mu. As well, this is a scalar, so it will be a product of the detector and some field that describes the detector. And the field phi. But the field phi should be calculated which is a phi of x, calculated on the detector, because that is a point-like particle. And okay, the detector is a field, but there will be also a function in front, which we call C of tau, which will be the switch on, to switch on and switch off the interaction. So that's an on-off switch, which means it's just a function that tells you that's that's just a function that will be 1 in a certain interval minus omega divided by 2 plus omega divided by 2 and 0 everywhere else, just to imagine that the interaction is switched on and off, and it doesn't last for infinity. Okay. At the end, we will send omega to infinity. So it will be large, but we want to imagine that we need a cutoff, because in quantum mechanics, maybe you remember, we are interested in the probability per unit of time. And otherwise, we will get infinity. So let's say that C of tau is equal to 1 for tau smaller than or equal to omega divided by 2 and 0 otherwise. And later, omega goes to infinity. Okay, now, what is the initial state of this detector, of the system actually? We will have that the detector will be in the fundamental state, and the field phi will be in a fundamental state. We call E0 the fundamental state of this detector, which is just an atom, and 0, phi, the fundamental state of the rest of the field phi. What is the final state? Any state, because we want to compute the probability of a transition out of nowhere, if you want, from the fundamental state to any state. So any state excited, it's an excited state for the atom, and the rest will be in any possible state, which we'll call generically psi. Okay. Now we want to compute the transition amplitude from one state to the other. The Bohr approximation what is it? We call it AI. That is equal to I times. Well, basically, we have to compute the average of the interaction between the initial and the final state, multiplied by I. So there will be an integral from minus infinity to plus infinity, but again the switch function here tells us that this is not lasting forever, so it's just an interval of size omega of what? We have to compute this average. So the interaction was C of tau, chi of tau, phi of x of tau. So this is the interaction, d tau if you want, because that's an interaction per unit time, average between the final state and the initial state. Well, everything factorizes here because the interaction factorizes the initial state and the final states factorize, so we can simplify this expression and write the average of chi of tau, the field of the detector between the initial states and the final state, times the average of the field phi between its initial and final states. So that is the object that we want to compute. Well, we can do something here, some standard manipulation that you should be used to, because this operator chi of tau can be written as e to the ih tau chi of 0 e to the minus ih tau, where h is the Hamiltonian of the detector only, because now we have factorized. So it's quite simple to compute this thing here. So this thing here can be written like that. And H, E0, EI are eigenstates of H. So e to the IHT will be e to the EIT tau, and then minus E0 tau. Then you remain with the average computed between, you remain with a time-independent factor that will be not terribly important. So the entire tau dependence is just this exponential, and this exponential will be important because we have to make an integral there. So let's rewrite AI. AI is equal to I times the integral minus infinity plus infinity d tau c of tau. Then there is this average which we have computed, which gives this exponential. And then another dependence on tau comes from the other sector of the system that we have to copy like that. So that will be computed in a moment. And there is a factor independent of tau that we can take out of the integral because it is not important anymore. Okay. Okay. Now, this is the amplitude. We cannot do much more about it. What we would like to compute is the transition probability. Which we call Pi. That is what? It will be the squared modulus of the amplitude, but actually, since we are not going to observe the final state of the field phi, that will be a sum of all final states of the field phi. Because we are going to observe only our detector. That's that's observing. So we will have to make a sum over these final states which we have no control over. So let's try and compute this squared modulus. Okay, so the modulus of that, well, first I has modulus 1, and then we will have a constant, which is this EI, the modulus squared of EI chi of 0, E0, which, by the way, we can take outside the sum because it doesn't depend on psi. And then you have the square of that integral, which is a double integral, so we have to write it down twice, and the integrand will have to be once exactly like that, and the second time we'll have to write its complex conjugate. So you have, maybe we can write it here. So you have two integrals. With two functions. And then you will have this thing with its complex conjugate. EI minus E0 will therefore multiply tau minus tau prime. And actually, everything we have written so far does not depend on psi, so we can even move the sum there. And we will remain with the sum of what? That thing. So let's see if we have enough space. Phi x of tau 0 phi times the complex conjugate of that, and you know how to write the complex conjugate. but the complex conjugate is calculated in tau prime. There. The scalar field phi is assumed to be real, so I do not need to complex conjugate the scalar field phi, I just need to write the Hermitian conjugate of the average, which is the complex conjugate. But now you see that you can use the completeness relation to get rid of the states you don't observe, because that thing is equal to 1. So maybe I can write it like this. That is equal to 1. So at this point you just compute, well, you can simplify the probability a lot. So you will get, first part stays there, unmodified. Then you have this double integral. Then you have the exponential. And then you have 0, the vacuum. Then you have phi in x tau prime. Then you have phi in x of tau. And then you have 0. And that is something we can write because this is the two-point function of a scalar field which we can assume to be free. That is the propagator. So when I have a free scalar field, and remember this is a description, very simple description of the gravitational field, so we assume that it is a free massless scalar field. And its propagator is well known. So in momentum space, it's 1 over p squared. And in coordinate space, when you compute the Fourier transform, it's 1 over x minus y squared. Actually, we cannot decide actually what this green function is, because this is, hope you know what I'm talking about here, but this is not a t-ordered product, because we have because of the way we have built it, it is vacuum, operator, operator, vacuum. And that is just, it's not the T-ordered product. It's precisely the two-point function. Which means that it is the retarded potentials instead of the T-ordered product. So how to give the retarded potentials? The propagator in the form of the retarded potential. So here in this formula I didn't write any prescription for 1 over p squared or that, but we have to supplement this with the correct prescription. So for example, in momentum space, that means that P0 has a plus I epsilon squared and the advanced potentials have minus I epsilon squared. The Feynman prescription instead, which we already met, but that is for the theory of scattering, that's the T-ordered product, is different because that is the Feynman prescription. But here we cannot use the Feynman prescription because we do not have the T-ordered product. In coordinate space, what are the equivalent prescriptions? Feynman becomes like this. Let me set y equals 0 for simplicity. So Feynman becomes 1 over x squared. This is 1 over x squared. And instead of having plus I epsilon, p squared has plus I epsilon, and x squared has minus I epsilon. Instead, in the case of the retarded and advanced potentials, it's x0, same way as p0 there, it's x0 which has a certain, it is like this, x0 has a plus I epsilon squared minus x space x squared. So what do we have to do there? There we have to use the formula for the retarded potentials, and then the integral can be computed. Actually, yes, okay. So pi is equal, let's write the integral. Then you have e to the I, ei minus e0, tau minus tau prime, times, well, 1 over 4 pi squared, and then you have 1 divided by what? X0 becomes x0 minus y0. But what is x? Now the role of x is x of tau prime, and x of tau is the role of y. So you have x0 tau prime minus x0 tau minus I epsilon squared minus space x tau prime minus space x tau squared. Okay. Now you just insert, instead of x of tau, x mu of tau, the trajectory of your detector. And first we will check that in uniform motion with constant velocity, there is no detection. So this probability will be equal to 0. And then we will see that every time the motion has an acceleration, and we will study the hyperbolic motion, which can be treated exactly, there will be a detection, and the detection will have a spectrum of the black hole. So, straight uniform motion. What does that mean? Well, first, the time, the proper time is time. And the trajectory will be x of tau will be x0, some initial position, plus some velocity, constant, times t, or tau, which is the same. So that is the trajectory. We could choose x0, we could choose, one thing that I wrote wrong is that in the Fourier transform you have a minus here. Yes. In x space you have a minus. It's important. You can check the Fourier transform. But yeah, the probability cannot turn out to be negative. So if you want, you have this. And what do you get there when we do this? So let me consider this object here. What is it equal to? So this difference here, for example, the space part first, x0 goes away, you just get v squared times tau minus tau prime squared. Minus, here you will have tau minus tau prime, actually tau prime minus tau minus tau, because minus I epsilon, there is a square, so I can put plus I epsilon. squared. Okay. So we will continue in 10 minutes and see that this is 0, and then we will move to the hyperbolic motion.